All right. So as promised, we didn't quite make it through all the examples for polar and cylindrical coordinates for F equals MA. It's kind of what we just did in class this morning. We kind of did normal tangent coordinate system, FMA, and then now we're doing polar and cylindrical coordinates, FMA. Right? This is just a brief little derivation. We talked about what the coordinate system looks like this. And we talked about what the acceleration looks like in polar coordinates. We have the acceleration component associated with r getting bigger. We have this centripetal acceleration for the change in direction. We have this tangential acceleration, and we have the Coriolis effect. So all of these things play into our equations of motion. All right, what they end up, our equations of motion look like, we sum the forces in the r direction is mass times acceleration in the r direction. You just simply put the acceleration in the r direction, which is r double dot minus r omega squared in that location, right? And then we do some of the forces in the theta direction, right? It's just going to be m times a theta, and then you just substitute in what a theta is, which is just r alpha plus 2r dot omega, and that just goes in there into our equation of motion. And then finally in the z direction, it's just the acceleration in the z direction. So we're in the middle of solving a problem. This is a collar that is on an inclined rod. If this thing isn't spinning at all, you can imagine this thing sliding down. If it's spinning too fast, it's going to spin, it's going to move up. And what we're trying to find is the minimum speed required for this thing just to hang out in this current location, right? And so what we did in class this morning was just kind of said, let's just look at some kinematics here. This is kind of like kinematics. What's the geometry of motion? Well, this thing's going to travel. If you look down at it from above, this thing's going to be traveling around in a circle kind of in this plane. Like it's going to be a circle in this plane. And so if we look at it from above, that's what this is, a plot over here. You can see that this thing's going to be traveling, that this collar right here is going to be traveling around in a circle as such, right? Our coordinate system is going to have, this radius r, and then er is going to keep going, and then e theta is in the direction of increasing theta. So this would be for an omega like this, right? And so that would be our e theta. The other thing to do in this drawing is just kind of show like what the radius of this is, this is 0.25 on the diagonal. And so its horizontal projection or vertical projection in this direction is just 4/5 times 0.25, which is 0.2. So the radius of this as it travels around is 0.2. Okay. And so then we said, all right, let's do first step, which is a free body diagram. I don't think I labeled my step over here. I'm going to clean this up a little bit. FBD. It's a free body diagram, right? The elements or the forces we have acting on it. We have mass times gravity acting down. We've got the friction force kind of acting. In this case, it's going to be up and to the right, and then we have a normal force up and to the left like this, right? So this is the friction force, and then the normal force going like that. Now, the reason we drew the friction force that direction is we're trying to find the minimum so that this thing doesn't slide down. So it's on the cusp of going this way, then the friction force is going to be acting up and to the right. If we were trying to figure out the maximum that you could go without the thing sliding up, then our friction force would be down and to the left. But since we're trying to figure out the minimum, it would be up and to the right. And so that's what we got going on. That's our free body diagram. Again, the thing that's a little tricky is the coordinate system, right? So, this over here is looking at it from above, and then this would be looking at it straight on, like it would be looking at it like this direction, right? So it'd be like it'd be this view that you see right here, right? Looking at it from this side over here. So ER would be going to the right. E theta would be going into the board, right? Or into the sheet here, okay? And what that leaves K direction being up like this. So this would be the K direction like that. And so we've labeled our coordinates, and we've got a good feel of what's happening here, okay? That's our free body diagram. Then we're going to do the equations of motion. M's. Those are going to look like, right? We're going to have the three different directions. We're going to have some of the forces in the theta direction. That's going to be equal to m times a theta, which is equal to m times r alpha plus or minus, what is it? Minus 2r dot omega, is that what it is? What do I got here? Plus 2r dot omega. Plus 2r dot omega. So that is what are some of the forces in that direction. In this case, I believe it says in there somewhere where it's going around at a constant angular velocity. Okay, constant angular velocity. The constant means that there's no alpha. Okay, and so this alpha term is going to go to 0. There is no increase in our angular velocity. There is no acceleration in that direction, so that alpha is equal to 0. Also, this thing is traveling around in a circle, so the radius, this radius right here, this r is not getting any bigger or smaller, and so r dot would be equal to 0. Okay. And so this would be equal to 0. And so there is no forces in the theta direction, right? And that's what the reaction is. Right? There's no forces in the theta direction. Which makes sense, right? There's no acceleration in that direction, which means there's no forces acting in that direction. If I had a force in that direction, then there would have to be acceleration in that direction. But in this case, there's no acceleration, so there is no force. All right. So then we look in the r direction. Some of the forces in the r direction is equal to MAR, which is equal to M times r double dot plus or minus 2r omega squared. Make sure I get those things in there correctly. Minus r omega squared. Oop, no 2 there. Wasn't done. Minus r omega squared. Okay. Again, that r is not getting any bigger or smaller. It's traveling around in a circle. So that guy, that r right there, r double dot is going to 0. So you're just left with these terms right here. And so we get, let's look at what's going on in that direction. So at this point, we could look at our free body diagram. So we need the left-hand side. What is the sum of the forces in the r direction? So I look over here and I say, hey, what do I have acting in what direction? So in the ER direction, right? I didn't do this. Usually I've been doing that lately as I've been breaking this guy into its components just to make it clearer. I'm going to go like this. And it's going to be like this. Right? And what is the triangle here? Oh, I guess I said before our free body diagram was done. It wasn't done. We left the dimensions out of it. I should have put the dimensions on this thing, but we did put the coordinate system. We did put all the forces, but what I didn't do is put the dimensions. So we will finish it up and put our dimensions on here. So this would be let's draw it inside here. All right, they give us this. This would be there's a 4 on the horizontal, so 4, 3, 5, and then over here, these legs would look like, this would be the 3, that'd be the 4, that'd be the 5 on that guy. So there's the dimensions, the angles that I have in there. But anyways, back to this. I think this is now complete. I got all the key dimensions on there. But you could figure out what that angle is given this, and then that would be the same as this angle right here, given that. Or you just leave it in 3, 4, 5. It's a little bit easier with that. So right now I'm in the process of summing the forces in the r direction. So I want this guy. And, I didn't break this guy down into its components. This guy's going to have components as well. Right. It's going to look like that. Right. So then the forces in the r direction is this guy and this guy. Just those two components. Okay. So those forces are going to be, we're going to have the friction force times 4/5. Right, that's this guy. And then that's in the positive ER direction, so it's pointed in the direction of that ER. And then we're going to have a minus the normal force times 3/5 is equal to negative mass times the negative r omega squared. And we're trying to find the minimum angular velocity. There it is, right? That's the r omega squared, or this is the omega rather. This is what I'm after, is that omega there. Again, kind of important to just like call it out every once in a while. What is it I'm actually after, right? I'm after that omega. And at this point right now, I'm getting close to it, right? But I got too many unknowns. I don't know what omega is. I don't know what the normal force is. I know that the friction force is actually going to be a function of the normal force. So right now I have two unknowns, right? I have the normal force and omega. So I can't solve the problem yet. So I have to go a little bit I have to keep stepping through it, right? I got one last set of equations I can use, and that's in the z direction. Make sure that I got yep. R makes good. Okay, so then the last direction would be the z direction. Sum of the forces in the z direction is equal to mz double dot. Right. So if we're trying to figure this thing out, where that this collar right here is not going to be moving up, it's not going to be moving down, and therefore it's not going to be accelerating in the z direction, right? If this thing was going to move up or down, it would be accelerating in the up or down direction. But in this case, we're trying to find it so it's not moving. And if it's not moving, that z double dot will be equal to 0. So this whole thing will end up being equal to 0. It's kind of a statics problem in that direction. And then this is equal to, Yep, okay. And so then let's look at what these forces are. I kind of like to do this. I like to write the equation and then I put an arrow to say, and then I start when I figure out what this is and then go from there. So some of the forces in the z direction. So just come over here to our diagram that's beautifully labeled. We've got mg in that direction. We've got our friction force in that direction and our normal force like that. So there's these three forces are all acting in the z direction. So we just write those things down. So this is going to be the friction force times 3/5. Right? Yeah, friction force times 3/5, and it's in the positive k direction. Then we're going to have the normal force plus the normal force times 4/5. That also is in the positive z direction. And then we're going to have a minus mg. That's the mass times gravity acting down. Okay? So that should be all of our components right there. And all of that is going to be equal to 0. Right? And so the only, let's do some substitution. This friction force is going to be equal to this, since it's not moving. This is going to be equal to, or the maximum it can become would be the normal force times mu k. The normal force times 0.2. I think they give that to us at 0.2. Yep. Is what that's going to be. So in this case right here, that's all of our unknowns. We have the normal force. It's going to be right here. Right, 0.2 times n times 3/5 plus the normal force times 4/5 minus mg, all that ends up being equal to 0. So the only unknown in that equation right there is the normal force. And so this tells us that the normal force is equal to, it's pre-calculated somewhere. 21.32 newtons. Right, everything, I do skip quite a few steps in here, right? I leave out, I don't simplify this equation down, but your mass, they give us that. Gravity, make sure you're using the right gravity. Right, so these guys, when you're doing this, mass goes in kilograms, g goes in meters per second squared, right? Forces go in as newtons, right? Just be very clear with it and use the exact units as you go through. Like I said, I'm really loose with my units, but I'm a doctor and I'm really good at it. Actually, but and I absolutely will make mistakes, but just be careful of your units, right? And the way I handle it is I think I put everything in meters, in newtons, and gravities in meters per second squared. and mass is going as kilograms. If you stick to that, everything's fine, right? Same thing in English units, everything's in pounds and in feet and in slugs, and everything's going to be okay. So just be very careful about your units. A lot of times the big mix messes, people mess up quite a bit, and it's simply just units. Okay, so now I have this this N right here, this normal force, all right? And so then this normal force can go right there. That'll be 21.32. And it can also go, I guess we can finish this off. This could be the normal force times 0.2. And so that'll go right there as well, that 21.32. And so then in that case, once you add that in, the only unknown is going to be omega. So once you get that, at that point right there, you solve for omega. Right, the last step is solving, and so omega ends up being equal to plus or minus 4.85. Plus or minus 4.85 radians per second. And that is what we were trying to find. Right? It's plus or minus, it makes sense that it's plus or minus, right? It makes sense that it's plus or minus because, you know, if you rotate that this way or if you rotate it this way, you can imagine it doesn't matter which direction you're rotating it. You can rotate it either direction, it would still be the minimum. If you go below this, then this collar is going to slide down. Right? It's going to get this friction force, this normal times 0.2 won't be enough to hold it up anymore, and so it's going to just slide down. If you go faster than that, it'll just kind of be stationary. There'd be a range. If you speed this thing up, you'd finally hit another one where this thing is going the other direction. And you could solve that, right? What you would do, if you try to find the maximum omega so that this thing doesn't slide up, you would just simply change your free body diagram right here, make this friction force act this direction, and then redo your equations of motion down here, and then it would tell you the maximum force that would be required in order for that to happen. So, the maximum speed required, or the maximum speed such that it won't slide up. Okay. All right. That should be it. Oh, no, that's it for that one. Okay. All right. There's that sucker. All right, the next one, very similar. Okay. It's a very similar problem. This too would be polar and cylindrical coordinates. It also could be done in normal tangent since things are traveling in a circle. But this is a very similar thing where this is just a rod and there's a string with a ball on the end of it. And you have this omega thing. So you're spinning this thing around. So this thing is traveling around in a circle, right, into the board as you see here. So a very similar thing. So if we're going to look at it from above, establish a coordinate system, do a free body diagram, and move on. Okay, you can imagine if you slow down, this angle of 85 degrees would change, right? It would get less. If I sped up, right, it would start approaching, a 90 degree, right? And so we're trying to find the omega required to hold this at 85 degrees, all right? So again, like I said, I like to look at this thing in terms of a circle. Say, like, what if I'm looking at it from above? Above. Right, what does it look like? Well, if my particle on the string is out here someplace, we can label our coordinates, right? If it's rotating around to the omega, so you're going to have, again, E theta in that direction, ER pointed out, ER hat pointed out, and then this radius, right, that R is going to be equal to 0.4 times the cosine of 85, or sine of 85. So 0.4 times sine of 85 degrees. And so this ends up being equal to 0.398 meters. And again, I these problems I do like to just lay this out so that I can see what my coordinate system is doing, and then I can figure out what this what my radius that actually rotates around in a circle is going to be. Right? And that's based off of this guy. So sine is opposite over hypotenuse. If that guy's 85, yep, so opposite. So it'd be sine 8. Yep, 2.398. Okay, so that's that. Next step when we do these things, the free body diagram. Like I said, this is very similar to the previous problem. Free body diagram. Isolate our mass. Again, these things should just be dots. Force is acting on, what has been doing that? My object is being black. Force is acting on this gravity. Mass times gravity. And then you have this cable. Back that direction. Right. And that's it. No normal force in this case. All we have is the tension in that rope. Okay, or on that cable or whatever it is that the problem statement says this. You have tension going back that direction, right? So then we're not done with this yet. We have to break this thing. We got to put our coordinate system on it. In this case, my ER is going to be going out like this. Right? And again, right, we're looking at this thing this direction, looking at it that way. And so it's going to look like this, which means the ER is going to be going out to the right. E theta is going to go into the board. And this direction right here, it's going to be the K direction again. Right? You could have done this one with no tangent coordinate system. It works that way too. Because it's as long as something's traveling in a circle, you could do either one. Okay. Still not done though. We have to put in, right, like again, I do like to break this thing into its components. Right, these two guys in the K direction and the ER direction. This angle right here is 85. So that should be my free body diagram. I didn't draw this to scale necessarily, but I got the key components out of it. Okay. Next step is to write our equations of motion. EOMs. Right. Some of the forces in the theta direction. Is equal to 0. Well, let's just write all this stuff. It'd be mass times R alpha plus 2R dot omega. And in this case, the thing is traveling in a circle, so R dot is equal to 0. And then there is no, it's at a constant omega, and so that means there's no alpha, so that guy's going to 0. So then again, we get the sum of the forces in the theta direction being equal to 0, right? If this thing was accelerating, there would have to be a theta direction. So if this thing was speeding up, right? If this thing was speeding up, as it was being whipped around, right? It started out with a smaller omega, and this thing was starting faster and faster and faster and faster as you went. This thing would be accelerating in the theta direction, which means that this tension force would have a theta component to it, right? Imagine this ball would be tailing behind a little bit, and then that tension force would be pulling it forward and accelerating it as it went around the corner. But in this case, since it's an alpha, since it's a constant omega, then there is no alpha in that direction. And so there is no forces in that direction. So this thing's going to constant omega, so this T is just going to be simply in the K and the ER direction. If it was accelerating, that T would also have a theta direction to it as well, right? But in this case, there's nothing. So the forces in the theta direction are equal to 0. Okay? You can go either direction. There's no order that you have to do this in. Right, you could do the Z direction next if you wanted to, doesn't matter. Times R double dot I did this last time, minus R omega squared in that direction. So then again, I draw a little arrow and I say, all right, let's look at the forces in the R direction. Right. And so then I go over here, look, I've labeled them here. I got this guy acting back like that direction. And that's it. Right. I have that component of T back in that direction. Right. So this will just become This will be the t times sine of 85. Okay. Ooh, it should be a negative t times sine of 85, right? And the reason it's negative is because ER is pointed that way and our t is pointed that way, kind of back and to the left, right? And so it's going the opposite direction of our coordinates there. So this is going to be a negative t times sine of 85. Okay, and that's equal to our mass times r double dot minus r omega squared. This r double dot is 0 because it's traveling around in a circle, and so r is not changing. Okay, that's as far as we can get with that right now. That's one of our equations. Right now, the unknowns in this is I don't know what t is, and I don't know what omega is. I'm after this omega right here. Again, identifying what it is you're after is pretty key. So I know what my mass is. I don't know what t is. I don't know what omega is. So I don't have enough right now. So I have to add another equation in here to keep going. So I just keep to solve this. So now I look in the z direction. Sum of the forces in the z direction is equal to mz double dot. And again, if this thing is we're trying to hold that angle of 85 degrees steady, that means this thing will not be accelerating up, it will not be accelerating down, and so that is just going to be 0. Right? So this is just going to be, all this is just going to be equal to 0. Right? So now we sum the forces in the z direction. We look over here, what do we got after the z direction? I got this guy, and I got this guy. I got those two z directions. So we should have those two components over here. We should have t times cosine of 85 minus mg. Because t times cosine 85, this guy's acting up in the k direction, so it's positive. This guy's acting down, opposite of the k direction, so that's a negative. And that's equal to 0. So in this, the only unknown that we have here, you can see the only unknown in this equation right here is that t. Okay? And so we could solve for t. The other way to look at it is, right, we got two equations, two unknowns, right? Here are my two equations, and my two unknowns are that omega and that t, right? And so that's usually what you do when you're solving these problems. You just kind of keep adding equations until you have enough equations that will equal the amount of unknowns you have. There's a pretty common theme throughout when we do work energy and stuff like that. We have to add in kinematics and things like that until we get enough equations, because we do get equations out of kinematics as well. In this particular case, we don't really need the equations out of kinematics because we got two equations and two unknowns, right? And so you could, if you wanted, right, plug this sucker right into my calculator, right? Obviously, you have to substitute in what your mass is and what your radius is, right? But you substitute that in, and your calculator do two equations and two unknowns if you want, if you know how to do it, right? And again, I'm not showing you how to do calculators. There's too many calculators out there, but I'm telling you, they can do these systems of equations, and you should learn how to use them, right? YouTube it, right? Ask ChatGPT, all sorts of stuff. They know how to do these problems, and so lean on that technology as much as you can, right? So if you lean on that technology, I could solve for what omega ends up being equal to. Right? If I can do t and omega. So based off of this, we can get t is equal to 134.9 newtons, and the omega that you get is equal to plus or minus 16.77 rads per second. Hey, but I think what they actually ask us, so they asked us for force in AB. The force in AB, that's T, 134.9. And the speed of B, they're not looking for omega, but they're looking for R times omega, the velocity. And so the velocity is equal to r times omega, which is going to be equal to 0.398, 0.398 times 16.77, and this ends up being equal to 6.67 plus or minus 6.67 meters per second. Okay, that is our answer. Okay, in particular, that's the tension in the string, and then that's the speed of it or the velocity of it. Okay, like I said, pretty straightforward when you stick to the plan. Right, this is our plan every time. Free body diagram, write our equations of motion, kinematics is required, not really much kinematics required in this one, and then the last step, solving. Right, if you stick to this, like literally, I've gone through your text, and where I get my exam questions from is I open up old textbooks from different authors and stuff like that, and that looks like a good one, and I work it out, I apply this methodology, I get an answer, and then that's what I end up putting on an exam. And so I literally solved almost every, this is 10th time I've taught this class. I've solved just about every version of these types of problems, and I can solve every one of them. Right? They're all just very straightforward, very procedural. Right? Lean on this solution method as much as possible, and kind of start stepping away from the intuition stuff. Right? This is all just particles right now, which is all just review. We're quickly going to move into stuff you've never seen before, right? In the next 3 or 4 weeks, we're going to move into 2D rigid bodies and 3D rigid bodies where things get real weird real quick. So anyways, good luck on your homework, and should be all caught up where we should have been had I not missed Monday for the funeral. Okay.